Today we explore the fundamental relationship between exponents and logarithms. Understanding these operations is essential because they form the basis of modeling growth and decay, and they frequently appear in both Paper 1 and Paper 2 of the IB Diploma examinations. By the end of this lesson, you will be able to manipulate complex index expressions and convert between exponential and logarithmic forms fluently. Let us begin with the laws of exponents for integer powers. These rules allow us to simplify algebraic expressions efficiently. First is the product rule. A to the power of m times a to the power of n equals a to the power of m plus n. When we multiply terms with the same base, we add the exponents. Think of this as counting the total number of times the base is multiplied by itself. Next, the quotient rule. A to the power of m divided by a to the power of n equals a to the power of m minus n. When dividing, we subtract the exponent of the denominator from the exponent of the numerator. The power of a power rule states that a to the power of m to the power of n equals a to the power of m times n. If a power is raised to another power, we multiply the exponents. The power of a product rule shows that ab to the power of n equals a to the power of n times b to the power of n. The exponent applies to every factor inside the brackets. Finally, we have two critical definitions. A to the power of 0 equals 1. Any non-zero base raised to the power of 0 is 1. And for negative exponents, a to the power of negative n equals 1 over a to the power of n. A negative exponent represents the reciprocal of the base raised to the positive version of that exponent. Let us apply these rules to simplify the expression. 5 to the power of 3 multiplied by 5 to the power of negative 6. Since the bases are both 5, we use the product rule and add the exponents. This simplifies to 5 to the power of negative 3. In the IB, you are often required to give your answer with positive exponents or as an exact value. Using our rule for negative exponents, this becomes 1 over 5 to the power of 3, which evaluates to 1 over 125. Now, let's look at an algebraic example. Expand, open bracket 2x, close bracket to the power of 4. Using the power of a product rule, the exponent 4 must be applied to both the constant 2 and the variable x. This gives us 16x to the power of 4. Finally, rewrite 2x to the power of negative 3 with a positive exponent. A common mistake is to move the 2 to the denominator as well. However, the exponent only applies to the x. So the correct simplified form is 2 over x to the power of 3. Today we are focusing on the concept of logarithms. Our learning goal is to learn how to convert between exponential and logarithmic forms. A logarithm is simply the inverse operation of exponentiation. It answers the question, to what power must we raise a base to get a specific value? If we have an exponential equation where a is the base and x is the exponent, this is equivalent to saying the log base a of b equals x. Note the constraints. The base a must be positive and not equal to 1. Furthermore, the argument b must be strictly positive because a positive base raised to any power will always result in a positive value. There are two common bases you will encounter. In the IB syllabus, if you see a log without a base, it is assumed to be base 10. The natural logarithm, written as ln, uses the mathematical constant e, which is approximately 2.718. Because logarithms are the inverse of exponential functions, their graphs share a very specific geometric relationship. Notice the graph of y equals e to the power of x in blue. It passes through the y-intercept at 0, 1 and grows rapidly. Now, observe the dashed line y equals x. If we reflect the exponential curve across this diagonal line, we get the graph of the natural log of x, shown here in red. Notice how the point 0, 1 on the exponential graph becomes the point 1, 0 on the logarithmic graph. This reflection property is the hallmark of inverse functions. Also, Observe that while the exponential function has a horizontal asymptote at y equals 0, the logarithmic function has a vertical asymptote at x equals 0. This confirms why the argument of a logarithm must always be strictly positive. Let's practice converting between these two forms. First, convert 10 to the power of 3 equals 1000 into logarithmic form. Identify the base, which is 10, and the exponent, which is 3. Following our definition, the base of the log will be 10, and the result is the exponent. Next, convert e to the power of y equals 5 into logarithmic form. Here, the base is the constant e. While we could write log base e, the standard IB notation is to use the natural logarithm. We can also use logarithms to solve for an unknown exponent using a graphic display calculator. Solve. To isolate x, we rewrite the equation in logarithmic form. Using your calculator, you would find that x is approximately 1.39794. In the IB, unless otherwise stated, always round your final answer to 3 significant figures. X is approximately 1.40. Let's look at an authentic IB-style question. Consider the expression. Part A asks us to show that P is independent of n. To do this, we need to write both terms with a common base. Since 9 is 3 squared, we can rewrite the expression, applying the power of a power rule to the first term. Now, using the product rule, we add the exponents. The 2n and negative 2n cancel out, leaving us with p equals 3 to the power of 1, which equals 3. Since the result is a constant, we have shown it is independent of n. Part B. Solve the equation log base 3 of x equals p for x. We found that p equals 3, so to solve for x, we convert this back into exponential form. The base is 3, and the exponent is 3. X equals 27. This multi-step approach is typical of Paper 1, where you must demonstrate clear algebraic manipulation. Let us review some frequent errors that can cost you marks in the exam. First, misapplying the negative exponent rule. 2x to the power of negative 3 is not 1 over 2x cubed. Students often move the entire term to the denominator. Remember, the exponent only applies to the base immediately to its left, unless there are brackets. The correct form is 2 over x cubed. Second, the freshman's dream error with exponents. A plus b squared is not a squared plus b squared. The power of a product rule only applies to multiplication and division, not addition or subtraction. You must expand the brackets fully. Third, entering logarithms incorrectly into the graphic display calculator. Log 50 is base 10, whereas ln 50 is base e. Using the wrong log button will lead to an incorrect numerical answer. Always double-check if the question requires the common log or the natural log. Here are some strategies to maximize your score. Always look for a common base. In many IB questions, if you see numbers like 2, 4, 8, or 3, 9, 27, your first step should be to rewrite them as powers of 2 or 3. This often simplifies the entire problem immediately. Show every step of your working. In Paper 1, the IB uses a method mark system. Even if your final answer is wrong due to a silly calculation error, you can still earn most of the marks if you have clearly shown the correct use of an exponent or logarithm law. Finally, pay attention to the exact value versus rounding. If a question asks for an exact value, leave your answer as a fraction or in log form. If it doesn't specify, round to exactly 3 significant figures. It is time to test your understanding. Please pause the video and attempt these 3 questions. Easy. Simplify 3x squared all raised to the power of 3. Medium. Solve 5 to the power of x equals 12. Give your answer to 3 significant figures. Hard. Solve the equation log base 2 of x plus log base 2 of 4 equals 5. Take a moment to solve these before we move on to the solutions. Homework solutions. Let's look at the solutions. For the easy question, we apply the power to both 3 and x squared. 3 to the power of 3 times x to the power of 2 times 3 equals 27x to the power of 6. For the medium question, convert to logarithmic form. X equals log base 5 of 12. Using a calculator, this is approximately 1.54. For the hard question, we first simplify the left side. We know that log base 2 of 4 is 2, because 2 squared is 4. Log base 2 of x plus 2 equals 5. Subtracting 2 from both sides, log base 2 of x equals 3. Now, convert to exponential form. X equals 2 to the power of 3, so x equals 8. To summarize the essential points from today's lesson, first, the laws of exponents are your primary tools for simplification. Always remember that the base must be the same to combine terms using the product and quotient rules. Second, the relationship between exponents and logarithms is an inverse one. Being able to fluently switch between the exponential form, a to the power of x equals b, and the logarithmic form, log base a of b equals x, is a core skill for solving equations. Third, remember the specific notation for common bases. Log x refers to base 10, and ln x refers to base e. These are the two most common forms you will encounter in both calculator and non-calculator papers. Finally, always maintain exam precision. Watch your brackets when applying powers to algebraic terms, and ensure your final numerical answers are rounded to 3 significant figures to avoid losing precision marks.